Good afternoon, ladies and gentlemen. My name is Anne Broadbent. I'm a professor at the University of Ottawa and member of the steering committee of QCrypt. It's my pleasure to moderate the panel of the industry session, more specifically on the topic of building a quantum computer. In the last few years, we've seen a huge increase in the industry's involvement in building quantum computing devices. The technology is advancing quickly, and some of the top talent is being recruited to work towards these impressive objectives. To tell us more about these recent developments, joining us today are three scientists working in industry and in academia. We will proceed in the following manner. First, I'll introduce each speaker. Each speaker will give a 5-minute presentation on their expertise. After the presentation, we'll have an initial round of questions that I've prepared for the panelists, and then we'll open the microphones, and we're looking forward to your questions and interactions. So without further delay, let me introduce our guests. This will be in alphabetical order. So first we have Runyao Duan from Baidu. He's been the director of Baidu Quantum Computing Institute since last March. Earlier, he was a professor and the founding director of Center for Quantum Software and Information at University of Technology, Sydney. He obtained his BE and PhD, both from the Department of Computer Science and Technology at Tsinghua University. He has been working in the field of quantum computing since 2001 and is the winner of the 2006 China Computer Federal Outstanding PhD Dissertation Award. He aims to become a simple and reliable person, and is in quantum superposition of scientist, interdisciplinary researcher, marathon amateur, professor, leader, and engineer. And the next slide will explain a little bit more what he means by simple. I'll just let you look at that while Runyao comes up to the stage.
Good afternoon. It's a great pleasure to be here, and thanks Annie for the introduction, and thanks Chang for the invitation to attend this panel. Actually, I'm very honored to be part of Baidu, is a leading Chinese search engine company, especially in China. And I really like the culture of the company, because the company said we need to be use the technology to make the world more simple. And also the value is to become simple and reliable. So then I think maybe it's a good idea to rewrite my CV. So I use this word to highlight some points of about myself. So I would like to especially today is to introduce a little bit about why Baidu is interested in quantum computing, and especially what's the longer plan of the company. Especially the Institute for Quantum Computing at Baidu was established exactly just almost 6 months ago, March 7. And the plan is actually very simple, because we believe that computing is very important. Quantum mechanics is also very important. But the most important thing is we need to, in a longer-term vision, we want to be everyone can understand quantum mechanics and can actually benefit from this. So this is why we have this very simple vision: is everyone can quantum, motivated by Charlie, because he sent me a video about anyone can quantum, but he's not here. I'm not aware him, but he said a nice video about anyone can quantum, and I was motivated by this, and I think we really need to have this long-term vision. And for the mission, it have 2 stages. The first stage is we want to have this Baidu Quantum. So that means that we want to build a world-leading research institute, especially on this quantum AI. And then for next part is for quantum Baidu. That means we will gradually, make the Baidu is become, some leading internet company that can support it by this, quantum technologies. So this is why I use a very simple words, Baidu Quantum and Quantum Baidu as the mission of the institute. And we are most interested in this QCrypt2018 topics, especially quantum AI and also quantum algorithm and architecture. So I use a Pentagon because this is my favorite, thing. I mean, because there are many things in quantum related to Pentagon, right? Especially this 5-qubit, error correction code for protective 1 qubit. Okay, so for this Pentagon, you can see the aim is, we have this architecture that's supposed to be the basic thing. I mean, so it can support our, applications, especially about AI. And then we really need this efficient algorithm to speed up, some very important core business of the company, especially like search. And also in future, I think for near-term computing, we need this, simulation and also secure computation. But I'd like to explain a little bit more about architecture. You can see that as an internet company now transfer to more like an AI company, where we are good at maybe this software and information technologies. So what we do is we not for a moment we're not directly building this physical devices, but instead we want to have this quantum hardware interface. So that can make sure people can easily access quantum devices through our platform. Okay, and also we want to have this unified programming platform and also distributed information processing model. So this basic thing can actually make sure people can access this quantum power. Okay, and then for the core application, I mean, I'm sure that machine learning will play a significant role. And of course, algorithm is definitely always the most important thing. So you can see we have a lot of things that you can find something you are interested in, but especially the darker triangle in the middle is especially the current focus. So the goal is to build the quantum technologies, so to make the company actually quantum ready, right? I mean, this is something we are really want to do. Okay, so here what I mean quantum capacity. Of course, the IPs are very welcome, and also patents, and also this students. These are all very welcome things. But most importantly, I want to say is we really want to have this top talents to join us, because we value this top talents, and we thought that's the most valuable thing of a company. And also we would like to participate in some grand research project, and also thought leadership, and eventually we develop key application into core service of the company, especially like cloud computing service and search service, and also this intelligent driving technologies, and also like education even actually, because education is also very important. Okay, so the second thing I want to say, because this is a panel discussion, so I would like to share something in my mind, because I know that this topic now is very, very popular, but then I'm sure there are actually challenges and opportunities ahead. They are simultaneously exist. So one thing is, I think the talents is the most, maybe the serious issue for the moment. When I was in university, like a few months ago, still I feel it's much easier to attract people to say, we have a permanent position. Would you like to come? And we never put this on the website, because we know we will receive maybe hundreds of CVs, because people would like to have this position. But if you say, I start a new institute at a company, would you like to join me? The pay is good, right? And then even so, then people will really to worry a lot. The reason is actually it's difficult to have the people that have all technologies about quantum mechanics, and also like computer science and mathematics, and know about quantum computing. That's rare and that's valuable. I mean, so talent is maybe probably the most the critical thing for the moment, especially in China. And the second thing is about the funding. I mean, we know that now there are lots of projects going on and investing a lot in this quantum. But come on, I mean, most money go to experiment. That's good, right? So that's still good. I mean, but the problem is about the architecture, algorithm, and AI application. This is only very, very small amount of money. So I think that's a big problem. We definitely need to put it more. And the last thing is about patience. What means patience? Patience means time. If we want to do some successful thing in quantum computing, we not just need to have this money. People always say, oh, if we have money, we can do anything. No, that's wrong. I mean, you need to have time as well. So people need to know that this is an information technology revolution. Nobody can escape. Nobody can say, oh, it doesn't matter with me. I mean, it's just your business. I'm not care about this quantum computer thing. No, it's a revolution. Everyone matters eventually. So I hope people can be patient and can actually contribute time and then give the engineers and the scientists more time to actually do their job and eventually make a successful quantum computer. Okay, so of course, last I would like to promote a little bit. I mean, we really value talents, and we really can contribute funding, and also we really have the opportunity to have the time to use to do quantum computing. So you're most welcome if you are full of passion and persistence, and also patience on this quantum information science. And send your CV to this email, quantum@baidu.com, and let's discuss. Okay. So thank you very much.
Okay, thanks a lot. Our second panelist is Shengyu Zhang. He obtained his bachelor degree in mathematics, Fudan University in 1999, a master in computer science, Tsinghua University in 2002, under the supervision of Ming Sheng Ying, and a PhD in computer science, Princeton University in 2006, under the supervision of Professor Andrew Yao. He then worked at NEC Labs America as a summer intern and in California Institute of Technology for a 2-year postdoc. Hosted by Professor John Preskill, Professor Lenin Schulman, and Professor Alexei Kitaev. He joined the Chinese University of Hong Kong as an assistant professor in 2008 and became an associate professor in 2014. Shengyu's research interest lies in quantum computing, algorithm design, and foundation of artificial intelligence. He's an editor of the journal Theoretical Computer Science and of International Journal of Quantum Information. He joined Tencent as a distinguished scientist in January 2018, taking charge of Tencent Quantum Lab. I also asked some of the speakers for a little bit of personal information just to make this fun. So apart from research, he likes general reading and sports such as jogging, swimming, and table tennis. He has 2 lovely daughters, and he tells me that his daughters like to help with his research by drawing really creative figures on his papers. So.
Okay, thanks for the very nice introduction. So I'm Shengyu Zhang. I'm from Tencent Quantum Lab. So let me very briefly introduce the Tencent Quantum Lab here. It's kind of interesting that it also looks like a pentagon. So we I didn't know this before. So the first direction is quantum AI or quantum machine learning, and we had some investigations on dimension reduction, generative models, and quantum neural networks. We also care about quantum simulation with potential applications in chemistry, material science, energy industry, etc. And of course, quantum algorithms is one of my previous research topics, and we hope to design novel quantum algorithms for combinatorics, optimization, and distributed quantum algorithms. And something very related to this conference is a quantum crypto or quantum related crypto. We actually have already some product in the Tencent Cloud service. One is quantum random number generator, and then the other one is a quantum key distribution. We also have the post-quantum or quantum safe signature schemes. And last but not the least, we started to study some quantum error correction, quantum architecture, or help the quantum chip design. So it's kind of like interface between software and hardware part. We have 6 members already, and a couple more joining. I tried to ask Runyao how many his lab has. He refused to give me the number. But well, Tencent has a culture of being very open. So, so you can see all of the education background, research areas, and collaboration opportunities. So finally, it's about recruitment. We hope to recruit people working at the locations of the Hong Kong, Shenzhen, or some parts of the United States or Europe. Currently, our members are mostly in Shenzhen, Hong Kong, but we are also open to other possibilities. And in terms of areas in this workshop, in this conference, we hope to get some applicants from quantum algorithms and quantum crypto. My personal research objective or research targets is to do something really interesting. And my interest is either theoretically very fundamental or practically impactful. I guess when I was a professor, whenever I wrote a proposal or when I wrote introductions to my papers, usually I try to claim that my results are theoretically very fundamental and practically very important. But in most of the cases, I'm not really sure whether my results are theoretically fundamental or practically important at all. But now after moving to industry, I think I do have a chance. I do see this opportunity that collectively we can do something better. So last but not least, after joining Tencent, or maybe I should say before I joined Tencent, I actually went to different companies to talk to a lot of people, especially the higher up people there. And I started to understand the huge difference between the cultures of all these companies. And for Tencent, I just took this picture from my name tag. And at the back side of the name tag is a value system or the Tencent culture. Basically, we emphasize on 4 things: integrity, proactive, collaboration, and innovative. I think it's also very important for the whole quantum computing community to be more open-minded, to collaborate more, and hopefully the academia and the industry can go hand in hand to push this whole very interesting quantum computing paradigm. Thanks. Sorry, I forgot to say that. Please submit your CV to this one instead of the one that you saw in the last talk and the next talk.
Okay, maybe people can submit to both. Spirit of collaboration. Thanks a lot for that. Our third panelist is Xiaobo Zhu, and he's been working at the University of Science and Technology of China, Shanghai, since 2016. And he was awarded a 1000 Talent Award Youth in 2013. Professor Zhu received his PhD degree from the Institute of Physics, Chinese Academy of Sciences. He has worked as a distinguished research fellow in the Institute of Physics, Chinese Academy of Sciences from 2013 to 2016. Professor Zhu worked as a senior researcher at NTT Basic Research Labs from 2009 to 2013. He's published distinguished papers in peer-reviewed journals such as Nature, Physics Review Letters, and so on. So, does the VGA work? Oh, here we go.
Thanks. So, so now I'm going to talk about something like the hardware, not the software. So I'm now working at the CS Alibaba and CS Center and USTC. So I will going to talk about something about the superconducting qubit. It's one of the quantum bit. Now it's one of the most promising systems. So since I only have 5 minutes, I just give a very brief review of our history and our plan. So in 2014, we start with the first exmo-transmo qubit, and at that time, the property is not good, the quality is not so good. In our system, the basic parameters is the lifetime. We call it T1 or T2. It's just on the order of several microseconds. After that, we first improve the quality of the qubit, like the something miss. Okay, now we can go to like 30 to 50 microseconds, and after that we can have a multi-qubit processor. And in 2016, we successfully demonstrate 10-bit entanglement. Until now, this is still the largest genuine entanglement in the superqubit systems. And we also demonstrate HH algorithm, which is solve linear equations. And during 2017, we have a quantum cloud access system. We can give the audience, we can supply quantum hardware service by this way. And now what we are doing is 24-qubit processor. We hope in 2020 we can realize so-called supremacy. Oh, I'm sorry, there's something didn't display. So after that, we hope during this, after the quantum supremacy, we hope we can collaborate with the software guys and develop some useful algorithms to really start the applications of the quantum computing. And for the next several minutes, I will just give a brief introduction for the quantum computing cloud access. This is in collaboration with quite a few institutes and Alibaba. Okay, so the purpose is, the hardware is always in the lab. So we hope in the future we can supply it in the cloud accessing, because in the future quantum computing, like especially the supernet computing, cannot like the normal computer like a PC. You cannot hold, you can not take it anywhere because it's work at very low temperature. So the only way to use it is cloud accessing. So we think it's really helpful to understand how good and how stable we can in this kind of very difficult hardware system. Because in a lab we can easily, we can use a lot of way to optimize the system. But if we want to supply a service to all the person, it is cloud accessing, so it should be very stable and very good. So it's really help us to test that. And I think another interesting point is because we have a real machine, a hardware, you can test in this kind of quantum computing. So that's stimulate interesting in all the peoples. And this kind of machine, in fact, including we made most of the part, including the ultra low noise platform and quantum compute process and the quantum computing control hardware and quantum computing software. So in fact, you can see this just like a traditional PC. You have to build up everything. Besides that, we need also an ultra low noise platform. That's extremely important because we are handling a quantum system. It's very weak. It's very easy to damage. It's very easy to lose the quantum informations. Thanks, Ali, they give us supply us the cloud server, and the user can use this cloud server and upload their code, quantum circuit, and then transfer to our software system, and we run the circuit, and we return back the result to the cloud server, and then the user can have the result. Currently, the process we opened is like a 12-bit system, and 11 of them are opened, and it is a 1D RAIN connection, and for single bit it has about 99.7% fidelity, and the 2-bit is about 95. And after we run about 4 months, we have executed about more than 3,000 tasks, and there's a user about 5,000 registered. But now we are testing the next generation of this sample. The performance should be much better. So it will reopened very recently. I think maybe 1 month or half month later. And I will show how to use it. It's just very simple. You can open the website quantumcomputer.ac.cn, and then you can input the name and password. Of course, you need to register before that. And then you can click the experiment and say, run a real quantum process. And then you can drag and place for the real quantum circuit. Because currently this is it's a very simple demonstration system. The circuit is not so complicated. You can use this graphic way to build up your own quantum circuit. The last is just the readout signal. And then you click run and input the number of average. After that, you need to wait some time because this is not a real-time system. You will upload your code to our server and we will run it. And after that, we send back the information. And you will see the result in a very simple figure. But if you want to know all the data, you can click download the date and you can obtain the full data. Okay, thank you.
Thank you. I'll invite the panelists to please be seated. And we'll start some discussions. Okay, so as I mentioned, I have a first round of questions. So first question for Wenyao. Why is Baidu interested in quantum computing?
Actually, that's a very good question. And actually, that's, the answer is actually a little bit simple, right? Because as a search company, the speed is most important. And we know that the quantum computer is actually good at this. And this is one reason. Another reason is actually in the future, we definitely, we will have a lot of data. And this data need a lot of, more security. So we need this quantum technologies to protect the data. And not to say is actually we also need maybe new ways to to explore this explore this the micro world, because as a search is not just to search some microscopic stuff, but eventually we will also went into this microscopic world and they do some thing. As an AI company, this is the most especially important. So I think these reasons are the key reason we really want to do this.
Okay, Shengyu, the question for you. What are the goals for Tencent Quantum Lab? What do you hope to achieve, and how are you going to achieve those goals?
I guess by and large, Tencent hopes to help to push forward the research and development of quantum computing and quantum computers. And well, I guess there are many ways to do that, but as I have already mentioned, one of the key cultures of Tencent is to emphasize the collaboration. So I think quantum computing is still at a very early stage, and to me at least, it doesn't quite make sense to close the door and just do all the stuff, trying to do all the stuff by one company or one university. It's simply impossible, I think, if everyone try to be close and be protecting, then maybe we will altogether ruin this whole very interesting field. So I hope to make more connections and collaborations and encourage more connections among many top universities around the world, as well as inside China. And I also actually hope to collaborate with other companies to push forward this. I think by and large, if finally collectively we all try very hard and speed up this whole process, then all of us win.
Okay, thank you. Xiaobo, you're representing the experimental side, and you told us about superconducting qubits. So
Yes.
I was wondering if you could tell us a bit more about this technology, and some people think this is the most promising technology, and why is that?
Okay. So in principle, superconducting way has good scalability because its process is like the semiconductor. You can print it like the semiconductor chips. So we can call it the processor. So in principle, you can scale to a very, very large numbers. But the problem is the quality of the qubit. That means the performance of the qubit. So you have to be very careful about kinds of noise. So we'll make effort to improve the precision of the control and the fidelity and lower down the error. And that's very challenging. We know since if for the service code one of the best it's a requirement for the lowest fidelity, you still need like 99.4 or 0.3 fidelity. It's really high fidelity. That means you can only have 0.2 or 0.5 error. So that's very challenging. But still, we in our field is indeed improved very quickly. So that's why I think big companies like Google, IBM, and Ali are very interested in this project. But I think still there's a lot of promising candidates besides the superconducting qubit. Maybe if they can overcome their big problems, they can solve it. Then maybe one day they can become more promising. Who knows? That's true. But for our way, for the superconducting way, I think we roughly know the problems from the engineering, how we keep the quality in a very small size, like several qubit, and enlarge it to like tens, hundreds, thousands, or millions qubit. That's a challenge currently. So we hope we have more like the semiconductor. We can increase number and keep the quality as well, and every year or every 18 months double the number like that. Then if it's true, I think it has, in the future it has a very good future. That's all.
Okay, thank you very much. We'll open the floor to questions from the audience.
Yeah, I have two questions. The first question maybe for all three of you. Well, what do you think about the standardization of quantum computation? Of course, I think probably I know some idea from Xiaobo, but still I think I want to know the opinion from you guys. And the second question is maybe for Ren Yao and probably for Shengyu. You say the payment is good. How good is it? You see the payment is good. How good is it?
That's the second question, right?
But the first question, we didn't heard it.
Standardization for the quantum computation, the hardware and software, that kind of thing.
Collaboration or?
Standardization.
Oh, standard.
The standard. Yeah.
Yeah, I think the standardization is now so far, right? Because I know you are actually actively working on this. Maybe maybe some of your colleagues, right? I think that's very important. Very important. And this is also one of the goals we want to achieve in our the institute's goal. But for the moment, I think there are a lot of things to do, and maybe a lot of things to work on. Maybe because if you want to make a standard, then I think we need to think about a lot of things, especially how about the scalability, right? Especially and because now we don't have the actual devices, and then we have to make this standard, and we need to think about many factors to make sure this will not be throw away just maybe 2 or 3 years. So I think this is it's very important, but also very, very challenging. So I think this need a lot, as Shengyu said, this is need a lot of collaboration. And also I want to emphasize a little bit, because just now maybe I didn't mention enough. Actually, the Baidu is a company that the most actually is engineers culture. So that means the most important, of course, many people are important, but the engineers is especially respected in the company. So this is why we're actually quite open, because technology is very something that you need to be very open. And for me, I actually already practiced this, because I already have the collaboration with maybe Australia, Europe, UK, and also Singapore, and also US in last few months, and many activities still ongoing. And also with Chinese, some top research institutions and also universities. And also we also offer opportunities for like the visiting professors, or some, if you want to spend some time at the company, to know about, to experience, different culture. all welcome. Also for student internship, right? And also for research projects, we are also very open. So this is why I feel it's very, very expensive in the last few months, especially my intern student also very busy because he helped a lot. So I think standardization will be very benefited from this kind of collaboration. And eventually, these people can form some kind of quantum social network, and they actually sit down and think about, to talk about what's the best for the students for certain technologies. So I think that's my opinion. Yeah. Thank you.
Any other comments about standardization?
I don't know whether it also depends on the area. I guess for like PQC, maybe it's really, or at least some parts of the PQC is already probably at the stage of the standardization. But maybe for some other areas like quantum algorithm, quantum complexity, this whole issue of the standardization is probably not quite there yet. We still hope to develop very novel quantum algorithms. So I guess it also depends. Maybe in the hardware, some parts there are these issues, but or we are still at a very early stage and shouldn't talking about this.
Okay, not very early. Not very early.
And as for the second question, either we could do a multi-party computation or zero knowledge proof so we can learn some information but not all of it, or maybe we can just observe that these jobs were open and they've attracted scientists coming from really nice academic jobs, so it must be very interesting. Okay, other questions?
Sorry, as you said, for second question, we can discuss face to face, right? Yeah.
I also have two questions. The first one is, we all know quantum computers are still at least 10 years away. They're really far away. So from now to then, do you have a business plan such as you can convince your management or investors give you money and without any profit?
To be honest, I only hear business plan, right? So maybe you need to repeat the question. Sorry.
Okay. So my question is, we all know that real quantum computers are at least 10 years away. It's really far away. So you will not have any real product in the next 10 years to sell or to do anything useful. So do you have a business plan to convince your management or your investors to keep giving you money without asking you to making profit?
So similar like what is patient, I think, yeah. How patient is patient,
But maybe we don't need a full-scale quantum computer to have a business case. Maybe that's part of the question too.
Yeah, I guess there are a lot of headlines over the last 2-3 years, and it's kind of confusing, especially for people who are not working in this area. Even for people who work in quantum algorithms, maybe he or she doesn't quite understand the recent progress in the quantum hardware part. So I guess it's not surprising to say that I believe many higher up management people across all of the companies, not only Chinese companies or U.S. companies. I guess for all of the companies, if you talk to like the CEOs, maybe they don't really have that kind of background, but it doesn't matter. I think what's really important is to, at least for me, I think I'm trying to maintain a nice environment for doing research and doing collaboration with other parts. And one thing that is important is that I hope to convey the correct information and to get all of the managers inside this loop of the decisions. And so there, at least in Tencent, we constantly have this loop of the discussions with all of the people above me. Fortunately, like in Tencent, they had Pony Ma Huateng, himself is a very curious person technically, and he really likes to just ask a lot of questions. So and also I guess everyone, at least every Chinese uses this WeChat. So we really have a lot of discussions over WeChat from time to time. So I think it's important to let other people know that it's a long way. If you plan to get some commercial payoff within like 3 or 5 years, then maybe you shouldn't even start a quantum lab at the first place. But at least for Tencent, and I believe similar things should be true for Baidu and Ali, but at least I know for sure is that for Tencent, I think people know that it's a very long way, and we are doing fundamental research, and part of the achievement is to help the research side. And in terms of commercial feedback, even if there is, it's probably be something like at least 5 years from now or 10 years from now, and we understand that. And we need to make a lot of important decisions, and hopefully, all of the important people should keep discussing and make all these decisions together. So there's a whole dynamics, and just try to, let everyone know the precise information. Don't be misled by some of the headlines, and then try to make decisions together. I think at least that's a Tencent culture.
Maybe I can add a few things, especially my feeling. The first thing is about the business plan. I mean, of course, if you don't have a business plan, then I think we can't get the job, right? I mean, that's the first thing. I think Shui will agree with me. I mean, for long-term plan, right? That's the first thing.
Actually, when
okay, so you're lucky, huh?
No. I think I guess what I try to emphasize is that I don't believe any people, especially for the big companies, I don't believe any people really have a very exact, concrete, precise business plan for quantum computing. Because even in academia, we don't really know, like quantum annealer or a circuit-based quantum computer, which is better. And we don't really know, even if we have a fault-tolerant quantum computing, what are the important business problems that we can solve where the classical computer cannot solve efficiently, right? So I just don't quite see how we could hope all those business people really have a concrete business plan. I think a more realistic way is to consider to study the business plan along the way. And during this time, we have this passion and patience to support the fundamental research, and that's the Tencent point of view.
Yeah. So let me just answer this question. Maybe I think that we have different understanding about what means business plan. So if I change a different term like a strategic development plan, does that sound better? So I think what I say is that for a company, eventually you need to make sure this thing will need to something valuable. I mean, right? Either you can achieve that, or either you can show that you can't achieve that. So eventually you need to have this kind of I think at least for me, I think that's most important. Because otherwise, if we just say, we just want to do this field and without very clear maybe take 10 years, but we still need to know what we want to achieve. I mean, maybe some not that exact, precise, but still something. This is why I have something like Baidu quantum plan, quantum Baidu. Because the first thing, the Baidu quantum is something that's an institute. So we can definitely make sure we can build something. We can build some research institute. That is a very concrete thing. Maybe we can do that with 5 years or maybe 7 years, but we can eventually with something we can measurable, right? But another thing is like also maybe more vigor, but still people can feel that. People say, oh yeah, this is something you can maybe eventually you can reach that. I mean, so that's my feeling about this. So for a big IT company, I think that is something very important. We decide to invest on some fundamental research topic that may probably have huge real impact. I think that's something very, very important. But another thing I want to share with you is exactly like I started to know about quantum computing at the beginning of this century. So it's 2000. In the summer of 2000, I started to know about quantum computing. And why I choose this field? Because at that time, I read some articles, and people say, oh yeah, you see, maybe quantum computer will be built, and then it's a disruptive technologies, and then you will everything in classical will be changed. So I was worried about that because I'm a computer engineering major student. So I was wondering maybe after 10 years I'm still young and full of energy. So why I should not do something that is of the more brighter future, right? So I do that. But to be surprised to me, even after 18 years, we still have not achieved that. So clearly I was tricked, right? I was tricked. But another thing I want to share is you can see that this field has not been dead. But instead, it's become much, much more stronger. Because of why? Because more and more people have their more confidence. They believe this will be the right path to go. So what I say is, as a fundamental research institute inside a company, the most important thing is we need to make sure what we have done will build the confidence of the company, and eventually we believe this, this is something we will achieve, or we can't achieve, right? This, I think, is very important. So that means the business plan for me, or strategic development plan for, in general. Okay, so thank you.
Thank you. Xiaobo, do you have anything to add?
No, I just come from university, so we just basic research.
Actually, we all do come from universities at some point. Other questions?
So it's probably a question for all three of you. So how would you differentiate the sort of work that the company get involved in this quantum computing in terms of research and also?
Could you louder? So here I
sorry.
cannot- yeah.
So how do you differentiate the research a company like Baidu or Tencent do from the research that a university like Xiaobo, your group does in the quantum computing area? No, I mean, what sort of work? How do you differentiate?
Different what between the university and the company?
Yes,
Okay.
the scope of research in university and also the scope of work in companies.
Okay, for us, I think Ali is just sponsors, and they said they are not want to decide anything in our research. They just feel the quantum information field is very important, and is like you said, is the right directions. So they just sponsor us every year some money, and they just say, yeah, if you have some good result, maybe we can share the talent or the patent or such kind of technical things. But since he believes this is the correct way, so just sponsor us. And if we have some result, maybe we should at least acknowledge them or just indicate the lab. The lab is just called CAS Alibaba Quantum Computing Lab, something like that. So still, I think the pressure maybe comes from the competition from the other groups. So we need to become the best, because research something like that, scientific things obviously like that, you would like to be the first one, the best one. Otherwise, you cannot publish papers. And the publication is still important for us. This is for the academic way and not the industry way. So that's different, totally different. Okay, this is for me. Okay, I don't know.
Actually, yeah, it's good to ask the question later, right? But unfortunately, I have to answer now. Okay, so actually, for me, because as I said, right, a few months ago, I was still in university, so I know exactly what university are interested in. Especially when you're doing research, right? I mean, that is especially for many people I know. I mean, but then I moved to company, and then I spent a few months. Actually, the first few months is to talk to leaders of different different directions to make sure what they really need for this about this quantum computing. And then I realized that there are actually huge difference. Because for example, for university, is what you maybe eventually you're most interested is to have some discovery, right? Or have some new protocol, new algorithm, or then something you can publish, and then you can claim you already have some certain technology, right? In some sense, I mean. But actually, that is far from the engineering aspect. So that may be something have potential, but it's still far from to be useful actually as a technology. So because of this, for me, I feel we need to distinguish between what university and the research institution can do and what the company should do. A research institute as a company should do. So for this case, my strategy is to, for this very fundamental research stuff, that is maybe very likely have potential, but not have the certain answer yet. For this kind of thing, we probably contract with some top leader needing researchers to fund them to say, oh, can you research on this too fast, and collaborate actually in this. But for other stuff, that can maybe some they are already very good algorithm or my protocol. You need some engineering technologies to make sure we can build into some system, for example, or platform. So for this kind of thing, we did at the research institute. But I have to say is you can see they are actually in some sense they are in some superposition. So that means we are not totally excluded as this some discoveries at the institute. But at the same time, the guy you work with, I mean maybe the professor at the university, they also need to think about how to match your requirement. So in this case, we are in some superposition, but that's exactly what the institute will do. So I see the difference, but I appreciate the difference, and we want to make the benefits of the both sides, and to have reach some win-win situation, right? So that's my opinion.
Xingyu?
Yeah, I think it's a fantastic question. I guess I've been thinking about what are the important research problems and how to when you choose the research direction, what direction should you choose, and when you evaluate a research result, a research paper, how to evaluate. I think all these questions matter for each researcher. And after moving to industry, I think there's one big change, which is to consider the applicability. In university, I guess we can pretend to have some results that we claim to be very, very useful to billions of the people, but after you get the grant, you don't really care too much about anyway you can claim to complete all the objectives for the grant, but when you go to industry, you talk to a manager, things are not quite like that. You trust me, those people are very smart, and you don't want to do something silly. So I think one question that I asked myself many times is, I was a theoretician and I still love theory a lot. Among all the applicable problems, is there beautiful and deep theory? I think for math, the answer should be yes, but you may need to take a long time, like number theory. You have to wait, maybe you need to wait for 100 years to see key applications in crypto. But in computer science, maybe we don't even need to wait for a long time. I personally believe that there are a lot of important problems that lack deep theory, but still are practically very important. So now I hope to start to search for problems that are in the long term applicable and has some potential applications in the company like AI scenarios. But fundamentally, there are some theory problems that are the bottleneck to solve those. I think deep learning is in some sense is one such areas, and I hope to dig. And the other difference, I think I go to companies that, well, it's actually good to your research if you can take this advantage of not having this pressure of the publication. So in university, if you keep silent for 2 years, then people ask you, what are you doing? But in research lab, if you keep silent, in terms of publication, it's good. Your boss thinks that you are working very hard, so you don't have the time to publish paper. But well, you have to talk to you should let other people to understand what's going on. But by and large, I think in company you don't really have this high pressure of publishing papers. So that, this could be positive or negative, but there's definitely one path to treat this positively, to give yourself time to consider the really fundamental problems. And actually in industry, you also, when people look at you, they don't look at you as an individual. They don't look at you as a person with a bunch of PhD students. They look at you as a port to a bigger company where they see the opportunities of the investment. they see the opportunities of accessing your huge data, etc. So all these add up to facilitate your research if you can take this positively.
Thank you very much for those very interesting answers. Our time is up. Thank you, gentlemen. Please join me in thanking our panelists.
Okay, thank you for attending the very last panel. The last panel is on post-quantum crypto and QKD standardization. And my name is Masahide Sasaki of NICT, and played as a moderator. And today we have three panelists, Jintai Ding, but unfortunately he could not come because his flight was canceled due to the bad weather. But fortunately, we could find another leading figure of this field, Hong Shan from China, and he represents the post-quantum crypto community. And we also have a Wei Qi and Andrew Shields from the QKD community. Okay, so let me briefly mention the purpose of this panel. So we would like to know the importance of the standardization, and we would also like to see what kinds of activities and challenges are going on in standardization of post-quantum crypto and QKD. And we also discuss what are urgent and what are the next important tasks, and how to migrate from the existing infrastructures to the quantum safe infrastructures. And we'd like to also discuss if there are any constructive collaborations between post-quantum crypto and QKD. And let's take home a vision on our common goals. So this is our purpose of this panel. And let me briefly draw a kind of a picture which summarizes a Darwinian sea of industrial species. And it is said that from the invention to innovation, there are two deep valleys. One is the valley of death between basic and applied research. And also, there is a big valley, it's a Darwinian sea, in which various industrial species compete with each other to be a viable technology. And I think we are in the Darwinian sea. And there are various schemes in post-quantum crypto, including hash-based scheme, lattice-based scheme, and code-based scheme, multivariate-based scheme, and isogeny-based schemes. And in QKD, there are single photon-based schemes, continuous variable-based scheme, and entanglement-based schemes. And also there are already some strong species, symmetric key crypto and public key crypto. So I'm not quite sure the near future in 10 years or so, but standardization is a kind of a process to select the survivor of the fittest in the Darwinian sea. So today we'd like to what's going on in the standardization process and just share what's next, what's the next important tasks for this community. Okay, so let me first invite the first panelist, Hong Shan.
Hi, everyone. First of all, I like to say sorry for the Jintai because it seems that he always have trouble with the airplane. Because he cannot make up this presentation, so he asked me to give a talk. And briefly, I will give you the overview, what's going on, the PQC, especially the standardization in the past 10 years. Everyone knows that in the past 2,000 years, we always have the symmetric encryption, which means we always use the same key to encrypt and decrypt. The thing changes, and last 40 years, in the 1978, we have the public key encryption, which is one of the representative is the RSA and the ECC. So in this case, for symmetric encryption, we require the secure prior key exchange, which is where our QKD comes to play. Very important. Okay. And for the basic primitives, the PQC, the public key encryption, we do have some special function, which is we call it signature. That is for authentication. For instance, any software updates, we need the signature. So that's how we play the public key encryption. And of course, we can use it as the key exchange. And this kind of protocol or function is embedded deeply to our internet protocol. For instance, the TLS or SSH. And the question is, can we live without PQC? The answer is no. Why? Because everyone needs the software update or online shopping, even use your smartphone. So that's why we need PQC. We need PKC, sorry. And the key point is we can use it for the large-scale and long-distance network to build trust and secure our communication. Now, the story comes to the PQC. And as we know that, in the 2015, it was August 19, the NSA surprisingly made announcement that is they don't want, we call it the first generation public key encryption anymore, which is should be encryption package. And they ask to use the so-called quantum resistant algorithms to replace the old should be package. And also, the NIST has the responsibility to make the standard. So in 2016, February, in Japan, they launched the roadmap for the NIST PQC standardization. And the first NIST post-quantum standardization conference is held this year in Miami. So that's how they push the PQC standardization very, very quickly. And the requirement for the PQC has been divided to 5 levels. The first level, as you can see that, is strong at least as hard to be break as AES 128. What does this mean? This means even we apply the Grover algorithms, then it can be reduced to the length of the key size is 64 bits. So that's level 1 security. And the level 2 security is at least as hard as break as the SHA-256 and so on. And level 3, level 5, and 4, and level 5. And you can see that the last security, we require at least has had to break as AS256. And in NSA document, they thought this can be resist the attack from quantum computers, even we apply the Grover algorithms, because in that case, we still have the length of the key size is 128. So that's good enough. So we divide it to 5 classes. Okay. And as for the public key encryption, we have 3 functions or 3 types. And NIST classified it as 3 categories. The first is we use the public key encryption as a signature. And the second one is the key establishment, and which is specified by the special publication 856A. And the last function is encryptions or key transport, which is put on the document SP 856B. So no matter what kind of public key encryption, say if you use the RSA or ECC, they can always play the 3 roles here, or you use the PQC, and they still should have the 3 functions. And for PQC, usually we talk about the 5 categories. That is, thanks for the Professor Sakaki, he already mentioned that we have code base, hash base, multivariables, and the lat base, and others. So they are the main targets we focus on right now. And compared with the first generation of the public key encryption, RSA or ECC, the second generation public key encryption, let's say PQC, has some precondition and conditions. No silver bullet, which means each candidate's lattice base, code base, multivariables, or hash, they has some disadvantage and advantages. So for instance, some of them has problem key size. Some of them has problem of efficiency or usabilities. So not enough research on the quantum security. That's why we're looking for the help from our QKD group. We wish we can work together and make the quantum safe algorithms. So at this moment, even the comment from the NIST experts, they don't think there will be the single winner when they make the final standardizations. So that's the situation. Okay, and there is submissions, the first call, and you can see many of the submit the algorithms to the PQC standardization. Okay, so how about the industrial? The industrial is very urgent to put on their concern in this field. For instance, the Microsoft pick up some algorithms, and you can see the algorithms chosen by Microsoft, and ARM, Intel, and etc. They also choose some algorithms from the PQC and try to put on their first generation of the product at this moment. And that gives you the idea how the industry pay attention to the PQC standardization. The process of the NIST PQC standardization is following. 2017 November is our first call. And this year, the April, is the first conference held by the NIST. Next August, as second conference held by NIST in United States. And from the 2018 to 2019, they called it a first round PQC standardization. And they're supposed to hold the 2 conferences and to verify which one or some of them are good candidates. And to 2020 to 2021 is the second round. And hopefully, to 2023, which means 5 years later, they will finalize the PQC standards. And the only hope from our part is at that moment, the quantum computer will not come up yet. Okay. If we take away from the PQC industrial workshop in the crypto, and we will see that there are still lots of arguments existing between the industrial, even between the countries. For instance, the Microsoft, they focus on some algorithms which can provide the function of the confidentiality. For instance, they pay more attention to lattice-based algorithms or LWE algorithms. And for the Google or Cisco, they pay more attention to the PQC algorithms, which has the signature function. Why? Because the Cisco has a lot of software updates they required, so they need signature. And the different view exists between the United States and the European, even in our country. So we're still looking for what is the common standardization roadmap so that every country can share the benefit. And also, some people proposed the hybrid approach for transition, which is ECC plus PQC, because somehow we thought the general quantum computers, which can broken the ECC or RC, still, let's say, 15 or 20, even 20 years later. So at this moment, we still can apply the ECC plus PQC somehow to reduce the risk. Okay, so that's all the case, how the NIST standardized the PQC. Thank you very much.
Okay, the next panelist is Wei from Chinese Academy of Science Quantum Network, and he is a chair of the QKD subgroup of China Communication Standard Association.
Hello, everyone. It's my honor to speak here, and my topic is Introduction of Quantum Key Distribution Standardization in China. So let's begin from the industry, the development of the industry. You know, in 2016, the first quantum satellite, Mozi, was launched. In 2017, the from Beijing to Shanghai quantum backbone network was put into service. In the same year of September, the first Internet Continental Quantum Safe video conference was held between Beijing and Vienna. The distance is about 6,000 kilometers. And in this year, the plan for National Wide Area Satellite Ground Integrated Quantum Secure Communication Network is initiated and will be carried out by CAS Quantum Network Co. Limited. you know, standardization is important to QKD industry. Let's see this structure. You know, QKD, the basic layer is QKD physical network, then network management, and they support different sectors and different variant applications. Standardization is essential to ensure multi-layer, multi-vendor. So let's see in the standardization activities in the whole world. As early as 2008, ETSA founded 6 specifications about QKD, and in 2017, CCSA initiates the Special Task Force on Quantum Communication and Information Process. And in 2016, OSCCA initiates standardization of QKD-based network cipher machine. Also in 2017, China delegates initiate the study period of security requirements, test, and evaluation methods for quantum key distribution in ISO. Then let's turn to CCSA ST7. CCSA is China Communications Standard Association. In June 2017, CCSA established the 7th Special Task Group focused on QKD-based quantum secure communication. It has 46 members now. Operators include CAS Quantum NAC, China Mobile, China Telecom, and China Unicom. Quantum vendor includes Quantum CTEC and other vendors. ST7 has 2 work groups. WG1 is quantum communication, WG2 about quantum information processing. The mission of ST7 is to develop the QSC-related standards in order to promote the QSC network deployment and application in China. Its goals include flexible and widespread applications, economical, efficient, and robust network, reliability and security assurance. Its route is from use cases and requirements to network architecture and quantum layer. And this is the framework of ST7 QSC framework. We have 11 items ongoing, including quantum communication technologies and definitions. It is actually. And in December of 2017, China initiates security requirements, test and evaluation methods for quantum key distribution in ISO. The goal is to standardization of security requirements, security tests, and evaluation methods of QKD device under the common criteria framework. So that's the summary. The first, in the need of large-scale network deployment and commercial application of QKD, developing QKD standards, including link level, system level, security evaluation, certification, and so on, becomes urgent tasks. QKD standardization is a difficult task, which requires multidisciplinary cooperation and strong collaboration among academics, industries, and governments. We hope to cooperate with global partners to accelerate the development of QKD standards to promote the deployment and application of QKD network. That's all. Thank you.
Okay. Okay, let's invite the last panel, Andrew Shields from Toshiba. And he has been leading the standardization activities of QKD as a chair of ETSI ISC QKD.
Well, thank you very much for the introduction. And it's a pleasure to be here today to tell you about the work of the ETSI ISG in QKD. So the mission of the ISG is to develop group specifications and reports describing quantum cryptography and ICT networks. And we published several documents in this area on things such as QKD use cases, application interfaces, security proofs, module specification, ontology, characterization of components and modules, deployment parameters, and implementation security. And the ISG has a membership that's been growing quite a lot recently, actually. We now have over 35 organizations involved in the ISG. And they come from a wide range of different backgrounds. So we have several QKD vendors. We have network equipment vendors, network operators, system integrators, NMIs, National Metrology Institutes, that is, government labs, and academia. It's sometimes like herding cats with these 35 different organizations, but most of the time, actually, we get on quite well and agree in the general direction. And despite the E word being in ETSI, in fact, the official name now for ETSI is no longer the European Telecommunication Standards Institute. It's just ETSI, in fact, that's the official name. But ETSI always stressed that they have a very international profile, and they make standards for international markets and not just for Europe. And that's also reflected in the membership of the ISG as well. So we have members from China, Japan, South Korea, US, Canada, as well as Europe. And at the minute we have several areas of interest which we think are the highest priority for QKD technology standardization at the minute. So in particular, promoting interoperability between different systems through developing interfaces for the equipment. I'll explain a little bit about that later on. We're also interested in different types of network architecture and in standardizing that, including integration of QKD into conventional telecom networks and also software-defined networks as well. Another area is in developing standardized methods for characterizing QKD devices and QKD components. Clearly, that's very important. And then finally, in studying the implementation security of QKD, how can we ensure that QKD systems are made, designed, and built in a secure manner? Okay, so just to tell you a little bit about two of those areas. Interoperability is very important. So here our goal is to develop standardized interfaces, for instance, between QKD equipment and other equipment. And this means that we can then use QKD with different types of applications. It means a third party can develop applications which are based on that standard and will increase the pool of applications in the future. It means that different QKD systems can be used within a network, and also different application hardware, such as link encryptors, for example, can be used within an application as well. So these standardized interfaces are clearly very important. So one example of an interface that we should standardize, for example, is the key delivery interface. That's the interface between a QKD network and some application. So we try to make that in a standardized way. And in ETSI at the minute, we're working on two different approaches to make that standardized interface. It means that different users of a QKD network can then develop different applications which are based upon that standard. And we can also interchange different equipment, both the key generating equipment and also the equipment which uses those keys. And this is really very important for generating customer value. It means that it will stimulate the development of new applications which are based upon those interfaces. It also means that there will be greater certainty of supply of both components and devices in the future. Users will know that they can interchange the QKD equipment or interchange other parts of the network equipment with that from different vendors, give them certainty of supply, and will also drive down the cost of the technology in the future. Another very important area is implementation security. So, of course, we know the security of QKD can be proven. It has so-called information theoretic security. It can be proven given a certain set of assumptions. And what's very interesting about quantum cryptography is that these assumptions are all about the QKD devices that we use, and none of the assumptions are about what an adversary is able to do. It's not about the size of the computer or the other type of technology that they have available. So that's our unique selling point for QKD. But of course, the flip side of that is that we have to verify that these assumptions are correct, and in particular that we understand the operation of the QKD devices very well. So it means that our QKD devices should be resilient to so-called quantum hacking. There should be no active attack that an eavesdropper can do, such as shining light into the system, for example, to learn some information about the signal states, to give you one example of an active attack. And also, there should be no inadvertent side channels. So the QKD system should not leak any information on other degrees of freedom, which can give an adversary some information that we don't know about. So the ISG are working on cataloging different side channels and potential attacks on QKD systems. And recently, actually, we published this white paper that you see here, ETSI white paper number 27, which is available on the ETSI website. And it's about the implementation security of quantum cryptography systems. It's written for a general audience, which kind of gives an overview of that area. The ISG is also interested in developing standardized security evaluation procedures for systems, so standardized ways of measuring these side channels and also the types of attack that you can make on systems. And for developing documents that will be needed for a security certification process for quantum technology hardware. So finally, let me say that although our membership has been growing, we'd like to grow it even more, and you would be very welcome to join this group. The ISG is open to new members and participants. If you're interested in that, please get in contact, and our next meeting will be in Madrid in December of this year. Thank you very much.
Okay, thank you. And all the panelists, please be seated. Okay, so let's start the panel discussions. So let me start with the first questions to each of the panelists. And maybe first to Hon. And I'd like to ask how to select PQC schemes we truly have confidence. I mean, theoretical analysis or practical attacks, which is more important, you think?
Personally, I'm not talking about represent to Jintai. I just
Okay.
personally, I thought it's a very comprehensive solution. We need security, and at the same time, we need the practice. For instance, talking about the IoT, because in the first generation of the public key encryption, we don't have the IoT 40 years ago. But now, let's look at in the future. When we talk about IoT or Industrial 4.0, we need lots of lightweight encryption. So in this case, we don't it's not reasonable if we ask the algorithm as absolute secure in the IoT situation. So in that case, we need security and the implementation. So that's how we deal with the new situation.
Okay, thank you. And a question to Wei. In dealing with quantum safe issues, how do we see the relationship between post-quantum crypto and QKD?
Yeah, I think PQC and the QKD, they can use in different scenarios. PQC can be used in some place compatible with current systems, and the QKD can be used in some situations requiring for long-term securities. But QKD is, at least now, is not so convenient because it depends on fiber or space and a little expensive. But I think for the customer, the integration of PQC and QKD may be a solution.
Okay, thank you. And to Andrew, so what are the priority areas for standardization of quantum cryptography systems?
I think the two big priority areas are interoperability. Standards are always about interoperability. It's being able to integrate QKD systems into the network and to operate them with other equipment that exists in the network already. So that's clearly very important. And then the second area is the big area of implementation security. So it's very important to ensure that the technology is implemented in a secure way. And that's clearly something that we need standards for.
Mm-hmm. Okay, thank you. So now we would like to have any questions, comments from the audience. Someone's? No? Okay. So let me move on to the next question to the panelists. To Hon, how to evaluate PQC security against quantum attacks?
It's a very good and a very hard question. Usually in our group, we use the classical method to analysis if algorithms is secure enough. But things has changed in the case of quantum computing because somehow there are few people really understand what's going on behind the quantum algorithms. Because everyone knows at this moment we only have two classes of the quantum algorithms. One is a Shor algorithms, another one is a Grover. So why it's so tough? In the past 30 years, 20 years, nobody get new algorithms. So these somehow reflect the embarrassed situation. The people need get more deeply understand what is the quantum. And my opinion is once we have real quantum computers, doesn't matter is large scale, general purpose, or is a middle size, we like to use it to simulate the algorithms and see what's going on and see how we can choose a proper way to against attack from the quantum computers. No answer yet right now.
I see. Interesting suggestions. Do you have any comments, especially from the quantum computing specialists like Tencent, Alibaba, or the panelists in the last session. Okay.
Sorry, I don't have a question to the or a comment to this particular question, but previously I wanted to ask a question before you started that one. So I don't know whether it makes sense to ask this question now, or I should wait until this topic is finished.
I mean, we'd like to discuss why we could not find any further quantum algorithms for the past few decades since Shor and Grover's algorithms were found.
Yeah, so I don't have any comment on this.
Okay.
I have a question unrelated to this.
Okay. Okay, please. This guy?
I have a question about the quantum cryptography standards. So we know that that's a long ongoing process and it's very complicated. And what maybe additional efforts from the society can be done? How can we make it faster?
Yeah, that's a good question. So I think we do need lots of research to back it up on things like implementation security and security of QKD systems in general. So proving the security of new protocols and yeah, looking at ways that we can improve the implementation security. I think one thing that has been perhaps a barrier to making faster progress in the past is that people haven't been able to commit resources to working on standardization, because it does take a lot of resources actually to work on that area. So often there's a lot of interest in working in that, but when it comes down to it, maybe academics think, oh, that's not going to improve my H-index, or industrialists think it's not really going to help the bottom line. So somehow it comes a bit lower down in the priority order. But we do see that attitudes are changing, actually. I think as the technology comes closer to the market, many people realize that it's absolutely essential for the market to develop. And if we don't develop a market in quantum cryptography, we won't be having this conference perhaps in 5 or 6 years' time. So we've all got a role, I think, to play in this area. And that includes academics as well as industrialists too.
So we need to make like international collaboration and publish papers from the international collaboration, which will be highly cited, and all members of this collaboration will receive very high cited paper in their CV. Am I right?
I think that will help, yes. And we also need direct contributions to making those standardization documents. We need the underpinning research, but we also need contributions to making the documents too. I think the situation will change because funding organizations have realized how important this area is too. So I've seen in some of the recent calls, standardization and certification seem to be themes which are included in those. So I'm sure we'll see some acceleration in the pace of the development in the coming years.
Okay, Vadim, please.
A question to all in the panel. So I see attempts of standardization for QKD in different standards bodies, which are in some sense competing to each other. Isn't this spreading resources, or why? How do you view the different standards bodies working on the same problem?
So I think we definitely have to have cooperation between those different standards bodies. But yes, I would say I share your concern that perhaps if we have too many bodies working on the same things, we will be diluting our efforts. So unless there's a clear differentiation between what the different bodies are doing, I think we should work together on this problem. Because the standards will be global at the end of the day. That's what we want.
Wei, do you have any further comments on that?
Well, the only thing I can say is I will bring your question to the 6th ETSI, the QSC conference this November, which will be held in Beijing. So let's see what they thought and how we can cooperate between the PQC standard and the QKD standard.
How about you? No? Okay, any further questions? No? Okay. Okay, so there might be some questions. Okay, to Hon, how to select schemes that can serve broad, scalable usage in industry? You emphasize that not only practical security, but some usabilities, practicalities are really important. And how, reviewers screen the schemes in this respect?
As I said, different company has different opinion regarding the algorithms. For instance, the Microsoft pay more attention to the lattice-based algorithms, LWE, because they want to use this as a key exchange to make sure the communication between the two Microsoft end users can keep their security longer. So they pay more attention to lattice. And the Cisco or the other companies, because they are communication company, there are lots of customers need to update their software. So they pay more attention to the PQC algorithms, which has the signature functionality. So that's, they have a different opinion about the process.
Yeah, thank you for your answers.
I guess it must also depend very much on the application as well. So even for a particular primitive, an IoT application is going to require a very different algorithm to a high-end application.
Yeah, as I know, I don't think the NIST has the more energy to concern the lightweight cryptography, which can resist the attack from the quantum computer right at this moment. Because this is another very complicated problem. They have a different group, different divisions to deal with. One is the PQC standardization, and another one is the lightweight cryptography standardization. I don't know, as I know, they don't have the roadmap to see how cooperate at this moment. But that will be a serious challenge if we don't consider the lightweight cryptography, which can resist the quantum computers. That will be a very serious problem. But I don't see the roadmap from NIST yet. And I don't know what is the situation of the European. Do you have the same consideration for the lightweight quantum resistance?
To be honest, I don't know so much about that there, so I'm afraid I can't answer your question.
Yeah, maybe this is where the QKD somehow can play the role, right? Talking about the light.
Eventually, if we can make it very cheap, using chip-based technologies, perhaps one day it can be used for those sort of applications.
Yeah.
But I think we can make it very cheap, I think.
Good.
Yeah, good to hear some constructive discussions. Are there any questions from the audience? Okay.
Yeah, 2 years ago, I have asked Michael Mosca in the ETS workshop in Toronto. And maybe the same question still for Hong. I asked Michael that is there any proof or demonstration that the PQC is more secure than RSA in the classical classical attack? And the answer is no. And the second question is there any proof that PQC is more secure than RSA against the quantum algorithm? And the answer is no. But yeah, he said there is some progress, but there is no kind of proof. So I think 2 years passed. I can ask Hong, anything change or any new result? Yeah.
Okay. As I understand, PQC, I guess what you want to know is if the PQC has the quantum proof security, right?
Proof against the classical or quantum, any more secure than RSA?
The PQC algorithms, the lattice-based LWE, these kind of algorithms, we thought it is somehow the quantum proof in the sense that we can reduce the hard mathematical problem of the LWE and lattice-based algorithm to an NP hard problem, which cannot be, we thought, cannot be solved even by quantum computers. So that's how we thought the lattice-based LWE algorithms has sort of the quantum proof security in that sense. But be honest, nobody knows if the multivariable algorithms has such property or not. We just thought it is a very hard mathematical problem, and nobody find the fast solution to break it yet. And same case applied to the code base and hash base. So in mathematician side, we try to find out the short-term or mid-term solution which can replace very important security functionality in our internet. So that's how we standardize the PQC. We're looking for the short-term and mid-term solution, not long-term. Okay.
Okay. Any questions? Okay. Yeah.
Hi, I have a question about the standardization. As we already know, QKD already go to industrial steps, and several countries are planning to or already build QKD network. So the question is, right now we are focusing on the real implementation security. That's one of the major goal of the standardization. So which one should go first? The standard should go first, or we just build the network first and then verify the security later? Which is more urgent for us right now?
Sorry, I didn't quite catch the end of that. So which should come first, did you say?
Yeah,
what are the
I
two
mean,
options?
the standardization should come first, or we just build the networks first and verify the security later?
You know, I think it only really makes sense to make standards once you have prototypes of things. So if we're talking about network standards, we have to build a network first and learn from experience with that. One thing we've learned in the Etsy group is it doesn't work well if you try to make the standard before you actually have the product or the product prototype. So making that demonstrator is definitely the first task. But there are lots of things we can do already. So we're working on implementation of QKD systems. So we have several vendors of QKD systems. So that's something that can be tested now. We can measure the real side channels now, the real type of active attacks, and work on the standards in that area. And we can also work on the interoperability aspects too. Then I think the network aspects of how to put it together in the network is the next task when we have large-scale networks, which are already being built, actually.
Yeah, I think it's time to accelerate the standardization process because, you know, if we want to build a more larger scale network, attracts more users to lower the costs, we need more players, we need a standard. So I think it's time to accelerate the standardization of QKD.
Yeah, I totally agree. especially when we try to sell QKD systems to customers, most of the customers first ask, where is these standards? So it's really time to complete the standard. I think time is coming, so I'd like to ask all the panelists to say something, especially what is the most tough aspect of the standardization activities. I think standardization is really tough task. And could you just mention finally your honest impression or?
Okay.
Oh, okay. Yeah, thank you. So Wakey have to leave for flight. Thank you.
You haven't got rid of me yet. I'm still here, I'm afraid. So I touched on it earlier. I think we all recognize how important standards are, and we all have to work on that, I think. But it's really getting the time commitment from people to work on that, because it's often an unresourced commitment. So everyone thinks that standards are really important to do, but maybe it's better if somebody else does them. But we do see the attitude changing there. As it comes closer to the market, I think companies are much more interested in putting time and effort into that. And like I say, there are some government-funded projects now which are supporting that area too. So I think we'll see a big change and a lot more commitment there in the future.
Very good. Okay.
The only word I can say is big change is coming, because let's take a excuse me. Let's take a look at the internet protocol as an example and see how many works, how many tasks we have to do before we standardize the PQC. Because in the current internet, the IPv6, we need to replace many first generation public key encryption to the PQC, and we not only require the security, we also pay heavy attention to the implementation. And as I said, there is no single winner of all the algorithms. It's totally does not look like the first generation public key encryption, because in the first generation public key encryption, we just simply use the ECC, then it can play the role of the signature, key exchange, and encryption. But in the PQC, they have a different disadvantage and advantages. So there is no single winner. So it's a very tough task.
I see. Yeah, thank you very much. Actually, standardization activities are really tough, and there are several important requirements for cryptography, like confidentiality, integrity, maybe availability, and also some functionalities. And finally, we have to find some reasonable, sensible system integration by using the both schemes, because only single scheme cannot cover the whole requirement of the for the cryptography. I think this session would be useful to consider such problems. And thank you for your cooperation, and let's thank the panelists again.